exercise 4.1 and 4.2, looking at power functions and their transformations. We're going to be taking a look at the higher powers to begin with. And first of all, let's consider the format y equals x to an even power. We've got y equals x squared. And if we consider x equaling 2, the value of y is going to be 4. So we're going to have 2, 4. If we now consider y equaling x to the power of 4, then I'm going to have this shape created, which is steeper. If I consider x equaling 2, then the value for y that I'm going to get is 2 to the power of 4, which is going to be quite large. So 2 to the power of 4 is going to be 16. So that's why it's appearing steeper. And finally, y equaling x to the power of 6. Again, it's steeper. And if I consider x equaling 2, then this time I'm going to get 64. So I'm going to have the position 2, 64. So you can see as we increase the power, the appearance of the standard parabola is much steeper. And the same pattern appears for y equaling x to the power of an odd number. So this is just standard. There's no negative in front of the x here. So they're all going to be positive cubic appearances. So we're going to have x to the power of 3, then x to the power of 5, which will be steeper, x to the power of 7, which will be steeper as well. Transformation. So if we've got any function f of x and it becomes this function here where I've got the f part and there's the x part, with these transformation effects of capital A, N, H and C, then here's an explanation, a summary of what occurs. Just to remind you, I've got A. So what's going to happen here is that we're going to be dilated by a factor of the magnitude of A parallel with the y-axis. That is, every y value is multiplied by that number A there. And when I'm referring to the magnitude, I'm just talking about the size. So ignore the sign. If it's a negative, I just assume it's positive. I'll deal with the negative in the next step with the reflections. What's the effect of the n? That's the coefficient of x. So that's the number in front of the x, but within the function. Hopefully that makes sense to you. Here what we're doing is we're dilating by a factor of 1 on the magnitude of n, parallel with the x-axis. So it's 1 over. That's the important part. Now, if A is negative, then the entire graph is going to be reflected in the x-axis. If n is negative, then the graph will be reflected in the y-axis. So we've done dilations, reflections. Now what we've got to do is consider the translations. C, that just shifts the entire graph up or down. If it's positive, it goes up. If it's negative, it goes down. Now to work out the horizontal translation, I just take this entire expression here involving the bracket, make it equal to 0 and solve for x. If the number that we produce is a positive number, then we're moving in the positive direction by that amount along the x-axis. If the number that we produce is a negative number, then we are moving in the negative direction by that amount in along the x-axis. And of course we can use our CAS to graph these functions quite easily. And I always suggest that you define your function and then you go and produce your graph. The main reason for that is that when we're graphing it on paper, we may need to work out the exact values of the x-axis and the x-intercept and the y-intercept. And the only way we can achieve exact values is to use the calculator mode, not here in the graphing mode for exact values. We'll now take a look at some problems. A, f of x equals 4 lots of 2x take 3 cubed plus 5. Now this is in like turning point form that we're used to from last year, but it's the cubic point form or point of inflection point form. So we first of all got to consider the basic shape. It's a positive cubic. The point of inflection. So I look at this bracket here and I'll make that equal to 0 and that will give me the x value. This part here will be the y value. So I have 2x minus 3 equaling 0 to produce x equaling 3 on 2. And the y value is that part at the end there, so that's just 5. So the point of inflection will occur at 3 on 2, comma 5. Y-intercept, simply sub x equaling 0 into the rule to produce negative 103. X-intercept, make y equaling 0, so I've got 0 there. I now subtract 5. Divide both sides by 4. Take the third root of both sides, and remember that you can have an answer for the third root of a negative number. I then add 3, and now finally multiply everything by a half. And that there is the exact solution for the x-intercept. I've given this decimal approximate that you can only achieve on your CAS calculator. That's just to give us a feel for where we should graph it. But that there is what I write down. So looking at the graph, I've got that point of inflection. I've got the exact value of where it cuts through the x-axis, the y-intercept, and there it is written. Transformations, dilated by a factor of 4 parallel with the y-axis, dilated by a factor of 1 on 2 parallel with the x-axis. There are no reflections. We are translated 3 on 2 units, so I'll just take that there, make it equal to 0, and solve for x. Translated 3 on 2 units in the positive direction along the x-axis, and translated 5 units up. I can also refer to this translation as just being 3 on 2 units to the right. If we take a look at the graph, then you can see that we can go from negative infinity for x to positive infinity. So we say that the domain is just R, the set of all real numbers. And then the same thing applies for the y values. Just general notes, I did all this by hand, but I could use my CAS. It's important to remember the original function and those transformations. And when using our CAS to get the x-intercept, we just solve for f of x equaling 0. And our y-intercept, we just substitute x equaling 0 into the function. What's most important is that you define your function. For b, we've got the function y equals 3 over x minus 2 take 4. As you would know, that's just the hyperbola, the basic hyperbola. So I recognise the basic shape, it's a positive hyperbola. The asymptotes are going to occur at x equaling 2 and y equaling negative 4. Remember, with the hyperbolas, you just want to have the value of x that will make the bottom equal to 0. So they're stated. And in my next move, what I would do is put in the asymptotes and then sketch out the positive hyperbola shape. So what we're expecting is that for the graph to cut through the y-axis at a value that's less than negative 4, and through the x-axis at a value that's greater than x equaling 2. To work out those intercepts, just make y equaling to 0 and solve for x, so I get 11 on 4. And to get the y-intercept, just substitute x equaling 0 into the rule, and I get negative 11 on 2. So I won't show you all the calculations on that, you've done that numerous times. So let's now take a look at the transformations. We're dilated by a factor of 3 parallel with the y-axis. There's no dilation factor along the x-axis. We are translated 2 units to the right, and we're translated 4 units down. If we take a look at our domain and range, then what we've got going on here is we've got all values of x from negative infinity to positive infinity, excluding the asymptote. So we'd write that as capital R excluding the set that contains the element x equaling 2. And for the range, the y values go from negative infinity to positive infinity, but we're excluding y equaling negative 4. So we'd write that as R excluding the set that contains the element -4. And that's what we've got written down here. So we've got the function g of x equaling 3 lots of the square root of x plus 4 take 2. So firstly, let's recognise it's a positive square root function, so it's going to be in that shape. The endpoint, take this, make it equal to 0 and solve for x, so I get x equaling -4, that's the x value, and this here is the y value. So the endpoint is going to occur at -4, -2. That's there. And now to work out the x-intercept, I just make the function equal to 0 and solve for x. Y-intercept, sub x equaling 0 into the rule and get the y value. And there's my intercepts. And there's the shape from the endpoint. My domain, I'm going from -4, including that endpoint, all the way up to positive infinity. So I can just simply write that x is greater than or equal to -4. And for my range, I'm starting at -2, going all the way up to positive infinity. So I'm going for the range y is greater than or equal to -2. All right, looking at D, I've got the third root of 3x take away 5 plus 5. Now, I understand that you wouldn't have a clue of what this function looks like. It looks like this. And the only way that you would work that out is by using your CAS calculator. You could create it using a table of values, but that would be much slower, so just use your CAS there and you can see that that's the basic shape. In this, there's a kind of point of inflection just there. And we can locate that using a similar technique that we do for square root functions, cubics when they're in the point of inflection kind of format, or quadratics when they're in turning point format. So to work out the x value, I'm just going to take this, make it equal to 0 and solve for x, and the y value will be this 5. So you can see that my point of inflection is at 5 on 3, 5, and that's just shown here. So obviously I'm going to be cutting through. To get this -40, I simply make that equal to 0 and solve for x. And to get the y value, or the y-intercept, I simply sub x equaling 0 into the right-hand side to produce the y value. So I've got those solutions. And the easiest way of doing that is just use your CAS calculator. The next thing I need to do is describe the transformations. So what we've got going on here is that we're dilated by a factor of 1/3 parallel with the x-axis. We are translated 5 on 3 units to the right, and we are translated 5 units up. When I look at this function, I can see it goes from -infinity to positive infinity along the x-axis, and along the y-axis, -infinity to positive infinity. So I say that my domain is R, the set of all real numbers, and my range is also R, the set of all real numbers. E, we've got f of x equals -2 lots of 4x take 3 raised to the power of 7 plus 10. So what we're looking at here is a cubic shape, because it's got an odd power, and it's going to be a negative cubic shape because of that negative in the front. So you can see I've already started the sketch here, but that's that negative cubic shape. Location of this turning point, or not turning point, but point of inflection. Make this equal to 0 and solve for x. So I'd get 4x take 3 equaling 0. Then I'd have 4x equaling 3, x equaling 3 on 4. So the x value is 3 on 4, and the y value is 10. And that's shown here. To locate the y-intercept, just make the left-hand side, for the y-intercept, just substitute x equaling 0. And to work out the x-intercept, make the left-hand side equaling 0 and solve for x. Use your CAS calculator and you should get some exact values, and you can put those in here. So that there isn't an exact value, it's a decimal approximate, but that is an exact value. Transformations. We are dilated by a factor of 2, parallel with the y-axis. We are dilated by a factor of 1/4, parallel with the x-axis. We are reflected in the x-axis. We are translated 3/4 of a unit to the right, and we are translated 10 units up. And that's described here. As far as our domain and range is concerned, there's no restriction on it. We're covering all values of x and all values of y, so we say that the domain is R, the set of all real numbers, and the range is R, the set of all real numbers.